The majority of the water on Earth is derived from its original structure, and at the present moment the Earth is coated with 1,338 million cubic kilometres of water, covering 70% of the crust. There are constant invisible interactions between the atmosphere and the ocean, exchange of heat, momentum and water across the air-sea interface. In general, the atmosphere receives heat from the ocean, thus affecting the atmospheric circulation and surface winds, which in turn generates ocean currents and the large-scale ocean circulation. Ultimately, these processes are driven by the sun. Emitted energy of the sun is 3.8 times 10 to the power of 26 watts. However, obviously not all of this energy is absorbed or even reaches the Earth's surface. The albedo effect on the planet is the ratio of reflected solar radiation to the total solar radiation, and this is measured above the atmosphere. The accurate determination of planetary albedo is important in the calculation of the Earth's climate. On average, the global albedo is about 30%, however, the Earth is not heated equally. The albedo can vary because of the surface of the land, the elevation of the sun, and the distribution and type of cloud. However, surfaces such as dense vegetation, dark landmass, and the ocean all have a low albedo and therefore are more susceptible to absorb solar radiation. Seasonal changes occur due to heavy snowfall in the winter months in Eurasia, which increases the amount of radiation reflected. The equator receives the most solar radiation due to the tilt of the Earth. However, the global atmospheric circulation redistributes the heat and it is caused by the Earth's rotation and atmospheric cells are formed. Water molecules with enough energy at the equator break away from the body of water and rise in the atmosphere. As this happens, the energy is passed on to the air molecules, which also makes them less dense. This results in an upward movement of water and air until they reach the upper edges of the atmosphere. The air splits in direction north and south. As they travel in the upper atmosphere for long periods, the molecules cool down at 30 degrees north and south of the equator. The air becomes denser and sinks down in the air column. The airflow is split again, and the stream returning back to the equator creates a convection cell, and these two are called the Hadley cells. The stream that goes up towards the poles is heated by the land, and the solar radiation conducts energy, so the air rises again at 60 degrees north and south. The same pattern occurs, creating the Ferrel cells. This often occurs around the latitude of the UK, which gives us our unsettled weather. The weakest and less defined cells are the polar cells, and they are formed at the north and south poles. These atmospheric convection currents create generalized regions of pressure systems. Unlike water, air is very compressible and means that areas in the Earth's atmosphere have relative high or low pressure. Atmospheric pressure is the force of which a column of overlying air presses on an area of Earth's surface. Pressure systems cause difference in weather experienced on a day-to-day basis. However, the general climate is influenced by the pressure systems. As you can see, at the equator in Bali, water vapour is heated and condenses in the atmosphere, forming clouds. This is an area of low pressure, as the air is also heated and moves up and away, so the pressure in the air column is low. Where the air sinks, high pressure regions are produced over the subtropical oceans and the world's hot deserts, such as the Sahara in North Africa. Prevailing winds created by the atmospheric cells are the most common generating force that creates waves. Sudden large inputs of energy, such as landslides, can also be a generating force. Small waves return to undisturbed surface level due to surface tension created by the cohesive qualities of the water molecules. Large waves are restored by gravitational forces. As the wind blows across the water, the friction or drag between the air and the water interface creates wrinkles and then small waves called ripples or capillary waves. New ripples are constantly formed in front of each moving wind gust. The wind transfers the energy to the water, so the velocity and size of the wave is determined by the speed of the wind. A circular path or orbit is formed by the water molecules in the wave as they move forward. The wave motion does not extend far below the surface as the kinetic energy transferred reduces. Deep water waves are defined where the wave occurs in water that is deeper than half of the wavelength. Wave speed can be calculated from the wave period. Storm centers in low pressure areas create long, intermediate and short period waves. Long period waves move the fastest. As they travel away from the storm, the long period waves overtake the others, and this is called sorting or dispersion. At this point they are called free waves, as they are no longer affected by the wind. Short waves have less energy, so are more likely to die out, leaving the long period waves to reach the coastline in uniform lines known as swell. When the deep water waves enter shallow waters, the orbits are affected by the ocean floor. The base of the circular path drags against the bottom. This reduces the speed of the wavelength, resulting in the wave increasing in height and steepness. Shallow water waves are defined by being in water that has a depth of less than 1/20th of the wavelength. Waves as we know them are formed in the surf zone and are called breakers. There are different types of breakers. There are plungers that form on narrow, steep, sloping beaches and are characterized by a more sudden loss of energy. Spillers occur on wider, flatter beaches and lose their energy more gradually. Ocean currents are also driven by insulation and can travel at the surface as well as deep in the ocean basin. Currents can be affected by wind, rotation of the earth, the shape of the ocean floor, as well as temperature and salt content, depending on their depth. Surface currents are strongly influenced by the prevailing wind direction. This creates currents that rotate in circular patterns and are named gyres. The gyre direction is determined by the location in the ocean, as they are controlled by the Coriolis effect. Ocean gyres in the northern hemisphere rotate clockwise and in the south anti-clockwise. The water also transfers heat, so these affect the local climate. Deep ocean currents are mainly determined by salinity and temperature, creating the largest ocean circulation pattern called thermohaline circulation. As you can see, solar radiation warms the water at the equator in the Pacific. The water becomes hotter and less able to attach to salt molecules, and therefore less dense. They rise to the surface in the water column. When the surface water reaches the North Atlantic, it is cooled by the ocean's ice and cool weather, so the water becomes more dense and sinks to the depths. The current continues to travel back down the Atlantic basin until it splits up towards India or continues around Australia, where it is heated up and pulled back to the surface in a conveyor belt-like action. This causes upwelling in the North Pacific and therefore brings nutrients to the surface where plankton blooms occur. Tides are one of the only oceanic processes that is not directly affected by the sun, and instead gravity is the driving force. The gravitational power of the moon forces the oceans to bulge, and the rotation of the earth results in a rise and fall of tides. The moon orbits the earth in the same direction that it rotates, but orbits the earth slowly, and causes a 50-minute change in high tide each day. However, tides are not uniform, because as you can see there is a large tidal range in Cornwall. However, the Bay of Fundy in Nova Scotia, Canada, has the highest tidal range of any place on the planet. The tide there ranges from 3.5 metres to 16 metres and causes erosion, creating massive cliffs. This is explained by the dynamic theory, as it takes into account the effect of shallow water, continents, and partially enclosed ocean basins, which affect the height and speed of the tides. Understanding how this tightly coupled system works is critical to our understanding of climate and how it might change in the future. All of the forces at play are evidence of how all the natural systems on Earth are interconnected and rely on each other to function.